Welcome to this comprehensive guide on permanent magnet synchronous motors modeling, control and calibration. Throughout this video, we will break down the key concepts behind field-oriented control, space vector modulation, maximum torque per ampere and constant voltage constant torque, providing you with a solid understanding of their principles and how they synergistically work together in the PmsmFocSvmMix MATLAB Simulink toolbox available at ingimix.com. The resources available on ingimix.com can help you learn more about PMSMs, so be sure to check them out. We'll start by describing how the PMSM system looks like, then delve into the fundamental equations for modeling PMSM inverters and PMSMs. Following that, we'll explore the PMSM control based on the field-oriented control technique, and finally we'll talk about maximum torque per ampere and constant voltage constant torque for PMSM control calibration. We'll conclude by showcasing the PmsmFocSvmMix toolbox, a single MATLAB Simulink tool that brings together all these elements. Let's start by describing the PMSM system. The key elements needed to control a PMSM are the PMSM inverter, which converts the DC power of a DC power source into a three-phase AC power, a position sensor, which measures the PMSM rotor position, and at least two current sensors, which measure the currents in the phases of the PMSM. The rotor position and the phase currents information are used by the PMSM controller to determine the pulses for each transistor of the PMSM inverter needed to generate the desired torque. The PMSM system can be represented as a voltage source VDC, a PMSM inverter with 6 transistors in parallel to the DC link, and the PMSM with each phase connected to a leg of the PMSM inverter. Let's see how the PMSM inverter and the PMSM can be modeled from scratch. We will not use any Simscape library, just algebraic and ordinary differential equations. This will help you getting a deeper understanding of how these components work. Let's start from the PMSM inverter. The voltage of each phase referred to the neutral can be calculated from the DC voltage of the power source and the pulses applied to the upper transistor of each PMSM inverter leg. These can be then converted into phase voltages by simply subtracting the voltage of the neutral. Speaking about the PMSM, we have firstly to mention that it is generally modeled in the DQ reference frame, where the D-axis is aligned with the rotor's magnetic field and the Q-axis is perpendicular to it, as this allows to move from a system of 3 equations to a system of only 2 equations, simplifying a lot both the model and the control. Therefore, the PMSM inverter output phase voltages are firstly converted from the ABC to the DQ reference frame through the so-called Clark and Park transformations. After this, the back electromotive forces, the fluxes, and the currents are easily calculated in the D and Q axis through these equations. We will not enter in the details of each equation, but feel free to visit ingimix.com to get a detailed description and demonstration of almost all the equations shown in this video. From the fluxes and currents it is then possible to calculate the electromagnetic torque, while from the speed we can determine the friction torque. From the torque balance equation, it is finally possible to calculate the mechanical rotation acceleration, speed, and position of the rotor. For the future calculations, we can also switch from mechanical to electrical quantities just by multiplying the corresponding mechanical quantity with the number of pole pairs of the PMSM. The currents are then converted back from the DQ to the ABC reference frame and provided to the PMSM controller. Let's speak now about the PMSM control, and more specifically about the field-oriented control technique. The field-oriented control, also known as vector control, is a technique used to control permanent magnet synchronous motors and AC induction motors. It works in the DQ reference frame and uses mathematical transformations to decouple the motor's torque and flux. With this method indeed, it is possible to control the torque and the flux independently by acting on the currents in the D and Q reference frame. This allows for precise and independent control of the motor's speed and torque, resulting in improved performance and efficiency. The FOC requires different control loops. The voltage loop, shown in green, which outputs the pulses based on the reference voltages VDQ ref. The current loop, shown in yellow, which outputs the reference voltages VDQ ref based on the reference currents IDQ ref. The torque loop, shown in orange, which outputs the reference current's IDQ-ref based on the reference torque. The speed loop, shown in blue, which outputs the reference torque based on the reference speed when the speed control mode is enabled. Generally only the current and speed loops are closed, while the torque and voltage loops are open. For these, there is no feedback that is monitored to verify that the control is working as expected. In addition, each loop runs at different frequency, and generally the voltage, current and torque loops are much faster than the speed loop. The most interesting elements of the FOC technique are the torque-to-currents block, which outputs the reference current's IDQ-ref based on the DC voltage of the power source, the actual motor speed and reference torque. The voltage decoupling block, in which the back electromotive force is subtracted from the reference voltages generated by the current loop's PI. The space vector modulation block, which outputs the pulses based on the phase voltages in the alpha-beta reference frame. In the torque-to-currents block, the reference torque is firstly saturated based on the maximum torque that can be delivered at the actual speed, and then is converted into the reference current's IDQ-ref. The maximum torque is calculated through a lookup table based on the motor speed, while the reference currents through a lookup as a function of the motor speed and reference torque. In the voltage decoupling block, instead, the contribution of the back electromotive force is subtracted from the output of the current loop pi's blocks. In the space vector modulation block, the alpha-beta reference voltages are used to determine the pulses to be applied to the PMSM inverter transistors. All the calculations performed in this block are shown on the screen. It's now time to speak about PMSM control calibration, and more specifically about maximum torque per ampere and constant voltage constant torque. These techniques are used offline to populate the maps that allow us to determine the reference current's IDQ-ref as a function of the power source's DC voltage, reference torque and motor speed. In order to get an idea of how these work, let's consider a reference frame with the ID current on the x-axis and the IQ current on the y-axis. Let's consider the motor initially at 0 RPM and request a constant torque. Between 0 RPM and the so-called base speed, the ID and IQ follow the MTPA curve. When the speed achieves the base speed value at the considered DC voltage, all the voltage of the power source is used to compensate the back electromotive force and the voltage drop across the resistance of each phase. This means that after this condition is achieved, it is not possible anymore to increase the speed of the motor by moving on this curve. At this point it is necessary to move along the CVCT curve, which allows us to keep proceeding until the maximum current is achieved. At this point, it is necessary to move along the maximum current circle through a sequence of decreasing CVCT curves, until the ellipse corresponding to the maximum voltage is crossed. The region included between the curves previously described is the operational area that can be explored. The maximum torque per ampere is a strategy that aims to achieve the highest possible torque for each value of the current. The MTPA curve can be obtained by setting the derivative of the torque with respect to the ID current equal to 0. The equations for the ID and IQ currents along the MTPA curve are shown here. The constant voltage constant torque, instead, is a method that allows to find all the points in the ID and IQ reference frame characterized by the same voltage and the same torque. This allows to explore all the operational area between the MTPA, the maximum current and maximum voltage curves. The equations describing the CVCT curves are much more complex than the ones related to the MTPA, and therefore we will summarize them by saying that the ID current is a function of the PMSM speed, reference torque and DC voltage of the power source, while the IQ current is a function of the reference torque and ID current. Again, you can find a very clear description and demonstration of these equations at ingimix.com. The MTPA and CVCT equations can be exploited to generate the maps that output the ID and IQ reference currents based on the DC voltage of the power source, motor speed, and reference torque. As first thing, we can determine the base speed, which is a function of the DC voltage and the maximum current that can be drawn. Then, we can iterate each value of the speed and of the reference torque in order to determine the reference ID and IQ currents through the equation seen before. In particular, if the speed is lower than the base speed, we can use the MTPA equation, while if it is higher than that we can use the CVCT equations. In all the cases, it is necessary to saturate the currents so that the current magnitude and the voltage magnitude are within the limits given by Imax and VDC max. Here you can see the results of the calibration process for a very small motor with 7 Ampere maximum current and a 24-volt power source. For each value of the speed and reference torque, these maps output the reference currents IDQ ref and the predicted values of the voltage, torque and mechanical power. For each speed is then possible to determine the maximum and minimum torques and powers, also known as full load curves. Let's move to the PmsmFocSvmMix toolbox, which implements all the concepts shown before. Please visit ngmx.com to get a user guide of the toolbox, a detailed description and demonstration for the main equations used in the model and in the calibration tool, and the full Simulink model that will be described later. It also includes an optimizer based on the particle swarm optimization method for tuning the coefficients of the pi's. The Simulink model consists of 3 blocks: the user block, where the user can set the operating mode, like the speed control mode, torque control mode, current control mode, voltage control mode, active short circuit, 6 switch open, and the reference values of the speed, torque, currents and voltages. Then there is the controller block, which determines the pulses for the PMSM inverter transistors based on the FOC and SVM techniques. Finally, you can see the PMSM inverter and PMSM model block, where these components are modeled using the equations described before. As mentioned before, the PMSM controller includes different loops, each running cyclically with different frequency. Speaking about the model, I would like to note that it is completely written from scratch in Simulink. This will provide you with a great understanding and control of what happens in it. Here you can see the results of a simple simulation. In the first section, the user commanded the PMSM in speed control mode, and as you can see, the PMSM is following very well the target speed set by the user. At 1.75 seconds, the user switches to the torque control mode, and therefore the PMSM control starts following the target torque instead of the target speed. As you can see, after an optimization of the PI coefficients, the controller is able to achieve very quickly the set point set by the user. A demo version is available at ngmx.com. This allows everyone to play with the model and understand how this works. Here it ends my description of the PMSM modeling, control, and calibration. Reach me at ngmx.com to support me and get the PMSMFocSvmMix toolbox and other fantastic engineering tools.